record this meeting. Yes, hello. How are you all doing? So somebody's asking whether we'll go over conditional statements. Yes. This is the first thing we do. Okay, whatever. Use in 5 minutes maybe. Okay. So let's go to the slides where we ended up last time. Share screen. Okay. And thanks, TA Will, for moderating the chat today. Thank you so much. Okay. So, okay, this is where we end up last time. We introduced the notion of equivalence between two propositions. And we say that the two propositions, here capital A, capital B, which could be some compound logical expressions, are equivalent. Oh, sorry. Please mute yourself. That was a pretty abrasive sound. Okay. You're doing it again. Okay, hopefully you muted yourself. All right. Complicated compound expressions here, but they are equivalent if they have always the same truth values. So no matter how you instantiate the atomic expression, the propositional variables inside of these two expressions, then they always come out true. So notice, first of all, for this to be the case, the variables inside of this expression and variables in this one have to be the same. Okay, except there could be an expression on this side that could have some variable, except that this variable is essentially useless. For example, some variable participates here in the form of, like, let's say variable z, okay, which is not here. Like this one is on only p and q. And this one has some function of p and q and z. But the z is always like z or not z. Okay, in which case it's like always true for any z. So then you can like extend your notion of equivalence and say that these are still equivalent. Okay. What has just happened? Sorry. Okay, I hope that you still are seeing the presentation. Okay. So these two expressions are equivalent. This is what we did last time. And in fact, this is a famous law called De Morgan's law. So the law is this, that it precisely is the equivalence of these two formulas, right? So that for any P and Q, if to say that it is not the case that P and Q, okay, this is what this says. I'm contradicting a conjunction of P and Q. This is the same as to say that either not P or not Q. Okay, how can you convince yourself of this equivalence? Okay, here's kind of like a fast way. So so conjunction is more often false than true, because it's only false. It's true. The only time it is true is in one case and one case only, when P and Q are both true. So to state that, so this left-hand side is false only if this thing is true inside, right? The negation. And so that's the only case this is the left-hand side is false is if both of P and Q hold. Now let's check this side. Let's check that the right-hand side is also false only if P and Q hold. Where you're in luck, because disjunction. Sorry, I have like a pointer issues. All right, disjunction is false only in one case. In case both of these parts of this junction are both false. In other words, but that is the case exactly when P was true, so that not P was false, and also Q was true, so that not Q was false. All right. So all we do here is walk through the logical the logic table for these two expressions, but we just like do this only in our head, right, rather than sketching the truth table. So they are equivalent indeed. Okay, and look, this happens all the time, right? Because like think of this expression like this, a conjunction, as some condition. Like, for example, a condition to admit a person in a bar or to let somebody drive or what have you is that they are 18 years old, that's a P, and they do have a valid driving license, that's a Q. Okay, so now, you know, a police gets on you or whatever, some sort of system triggers when this is falsified, right? Or you're just rejected from the application in this case, right? So when this condition is false. Now, when is the condition false? Where if you don't satisfy everything the condition specifies, right? The condition specifies you have to do P and you also have to do Q to qualify. So it's falsified when this thing inside is falsified. What does it mean? Like one of these conditions fails. This is exactly what this says. It says that either the first condition fails or the second condition fails. If there was more, there would be a disjunction of not first, not second, or not third, or etc. Right? So the Morgan law is sort of immediate that it generalizes to the. And by the way, if you remember how we argued that why it doesn't matter to look at the order when you have a big conjunction, well, because the only way you can make it true is for all of these guys to be true. And look, on this side, if you flip it, so that would be the only time this is false. And if you flip it, well, the only way to make a big disjunction false is to falsify each part, right? All right. So now flip. Sort of a sister of this law, where we say this negation of conjunction is the same as disjunction of negations. Here we have negation of disjunction. And it's the same as conjunction of negations. Okay, so why is this? Again, a truth table you can make, right, and convince yourself of that. And now we're going to like sketch a truth table, hand wave it, right, in our heads. So now you remember the truth table for disjunction. It's almost always true. The only way to the hard case is to falsify a disjunction. It's like if you need to falsify it, then you're in luck. There's only one way. Both of these guys have to be false. Because you are negating this, so this means that it's easy to make this. So let's consider the only case where this is true, which is the only case that the inside is false, which by the laws of disjunction, I'm repeating myself, is this case. But the only case, right? So this is the left-hand side is this the only place is going to be true if both of these variables are false. Let's check that the same thing is true for the right-hand side. Well, great, because if you are trying to make the right-hand side true, you're in luck. It's a conjunction. It's rarely true, which is good for us here, right? Because we just have to check that this corresponds to this case. And it does, right? Because to make this conjunction true, both this and this have to be true. And the only way to make both of them true is when P is false and Q is false. So it's the same. Left-hand side and right-hand side are equivalent, right? And again, this happens in you know, this is a common thing. to express something as a one big disjunction. Okay, like for example, you give a drug to a patient if he has either a history of migraines or diabetes, right? So now you don't give, right? Like when are you going, like say, okay, this patient is okay, right? When this disjunction is false, but disjunction is false exactly in the case where all these conditions which make this disjunction here, which form this disjunction, are all false, right? So the patient does not have migraines and also does not have diabetes. And if there was more conditions, then the list would continue, right? So again, you can do this with the truth table, of course, but just these strategies, right, for like quickly falsifying something and realizing that the only way some expression can be either true or false, depending on the expression, is one case and one case only. That's a good, useful skill, right, to practice. Okay, here is the conditional operator. So an implication. When is an implication is another binary operator, right? It's an operator that takes two elements, and we denote it with P arrow Q, right arrow Q, and we read it P implies Q. Well, but there is other ways to read it. For example, if P then Q. And so whenever P happens, then so must Q. And there is actually many ways to render it. So the book will give you a list. You will see in a sec actually other ways to render this too. Okay, what is the truth table of this function? Or the function that takes two elements, P and Q, and says, okay, what is the truth value of the implication that P implies Q? And how does it depend on whether P and Q is false? Okay, this is what I don't understand what exactly happens. I don't know what happens on your screen. I hope nothing too drastic. And I hope now that we are back at the slides. Okay, if we lost them at some point. All right. So this is the truth table for the implication. We say that the implication that P implies Q is true, actually, regardless of the value of Q, but the minute P is false. Then if I say if P then Q, and P does not hold, then you don't even have to look at what Q is. It's true. So this is like, remember the song from the, maybe some of you know it, some of you don't know it, If I Were a Rich Man, from Fiddler on the Roof. If I were a rich man, da 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 da, you know, like I would do this and I would do that and I would do this. And perhaps the poor guy manages to do that, perhaps not. Well, all those statements happen to be ironically true because he's not a rich man. And now when both are true, then it would, you know, we declared the implication to be true. And the only way to violate an implication is to find a case where P is true, the hypothesis holds, but the conclusion of the claimed implication does not. Okay, so that is a one place and one place only where the implication fails. Okay, why, you know, what does this correspond to in English speech? Okay, because it doesn't exactly correspond to every way, you know, the way people use, if I do this, then I also do that, or like, if this is the case, then so is that. Sometimes that's exactly what they mean. Sometimes it is a sort of fallacy, as in they can, well, they can mean it, but maybe they don't. Maybe they're actually trying to play with you. So here is logic has a conservative interpretation, if you will. Okay, it's like implication is true unless directly contradicted. Okay, and the only way to directly contradict it in some sense is for the for the hypothesis to be true and the consequent to be false. So consider the following: M implies P, where M is you mow my lawn and P is I will pay you. Okay, I'm killing a chat window because it's like messes up my pointer. So hopefully we'll monitor it and speak up if there's something says like, you know, something completely off, right? But that you want me to react to. All right. So the implication is you mow my lawn and I will pay you. Okay. Now let's look at the possibilities. The hypothesis is either true or not. So you either mow or you don't mow my lawn. And the consequent is either true, I paid, or it's false, I didn't. So if you mow it and I paid you, then this implication, the status of this implication is true. Okay. If I directly contradicted this, so you mowed, but I didn't pay you. Okay. So this statement is clearly false. You mowed, but I didn't pay you. I've lied. Okay. So you assign false to this implication. But if you don't mow, that's the evaluation case. The hypothesis, it is the implication, we declare this to be true. Okay. And now look at this. If you want to test whether an implication holds, you can look at the two strategies. First of all, look whether the consequent is true. If it is, then you don't need to bother with the hypotheses. So a statement like something weird implies 2 equals 2. Well, all I need to know is that 2 equals 2 is true, and the implication holds. And the implication could be of the form, you know, if you fly to the moon, then 2 and 2 equals 2. Okay, I guess some people flew to the moon. All right, so flew to the, you know, near planet, near solar system to ours. It could be any nonsense here. As long as you say la 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 if da 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 and this implies 2 equals 2. All I need to know is that 2 and 2 equals 2 is true, and this whole implication is true. Conversely, if you can also look at the hypotheses and say, well, if the hypothesis is false, then conversely, I don't have to look at whether the consequence is true or not. The moment hypothesis is wrong, the implication is true. So basically, if I say if 2 is equal to 3, that's my M, then I can say any nonsense here, and the implication will remain true. Okay, so the statement of the form, if 2 equals 3, then you don't even have to listen to what happens after then. That implication is true, no matter what follows the then part. Okay, so here is a beautiful law that you might find useful. A conditional P implies Q is equivalent to saying that either hypothesis is not true or the consequent is true. That's what I did on the previous slide. That's exactly the case, right, where to evaluate the value of this, I can have two strategies. Look whether the consequent is true. If it is, then this is true no matter what P is. Well, this is what this part says. I don't really care about this. The moment Q is true, consequent is true, disjunction is true, you don't have to bother with this part. Another strategy is that the implication is true the moment hypothesis is false, this is the if 2 equals 3, then whatever. Well, let's look at this hypothesis and let's see, it's not true. So I don't need to bother with the consequent. The implication holds. Well, that's this part. Okay, so also truth tables, right? Like they just prove to you on the piece of paper that this is exactly right, what I was just saying. Yes, because the truthfulness of this corresponds to the two cases. The hypothesis is false, and these two rows, the consequent is true. Okay, or these two rows, right? The consequent is true. All right. So why would you bother with this? Because, for example, perhaps you have some things written as a bunch of implications, and it gets hairy. What does it mean that like this implication holds, or some other one does, or not some other one, And then, well, I know that all these implications are equivalent to a certain form of disjunction. Perhaps substituting implication with these disjunctions will allow you to reason about some larger Boolean formula. So that's one way of looking at usefulness of this. So here is an example. If C is I'm saying if an integer is composite, then it has non-trivial divisors. Alternative way to say it, and it would be the same thing, would be to say that an integer either has non-trivial divisors or it's not a composite. Yes. So if I say it is the law for every integer, if it's composite, then it has divisors. Then it's the same for me to say that there is two cases. First of all, an integer might not be composite. It's prime. And another case is, and that's the case of where you're concerned with this integer being a composite, actually, is that it must have non-trivial divisors. Okay, it's saying the same thing, right? Contrapositive. So contrapositive is an operation that is applied to an implication. Okay, so it's like we say, okay, we have a formula in an implication form, and we say, here is a contrapositive of this formula, and it is defined to be an implication that goes the other direction on negated statements. So a contrapositive to saying P implies Q is to say that not Q implies not P. So look at an example. If I say, if Susie studies, then she passes the class. Then consider a contrapositive of this, which would say, if Susie doesn't pass the class, then she must have not studied. And if you think of this, it's like, actually it's the same thing. It's saying that if a condition that someone studies holds, then it immediately triggers, like a domino, another variable, which is dependent on it in the sense that if that one goes to true, then the Q must have kicked into true. So if she studied, then immediately she must pass the class. So what happens if she doesn't pass the class? Well, you can conclude that she must have not studied, because if this is the law, if this is true, if it always is the case that the minute somebody studies, then they pass, then if you observe them not passing, well, either this implication is false, but we are stating the implication, so I guess it's true, then the precedent, so the hypothesis must have been false. Another way to say it, contrapositive is equivalent to the implication. And again, you can look at the truth tables, and you can see that how can you quickly convince yourself this is true, that these are equivalent? Well, what do you know about the implication? Let's look at the only place implication is false, right? Because like disjunction, implication has a truth values, which is only 0 is only in one place only. It's when hypothesis was true, but consequence was not. So P true, Q false. Let's look at this side. Well, there's an implication. Good. So there's only one row in a logic table, which will make this false. Which row is that? This part must be true, and this part must be false. In other words, Q, because it's a flip, for not Q to be true, Q must be false. For not P to be false, P must be true. Q false, P true. That's the same case as which contradicted this part, right? So the only way to falsify both left-hand side and right-hand side is the case of P true, Q false, right? Okay. Now this contrapositive is used all over the place, right? So this is a kind of a logical thing that we have. Okay, if somebody said that some action will bring certain consequences. If these consequences didn't happen, then the action must have not happened, right? Okay. It's yeah. Okay. So you have the truth tables here sketched for your enjoyment as you go through the slides at your leisure, or right now maybe you sort of see this straight away, right? Okay. Okay, I guess I forgot that I had these animations. All right. So another way to derive the same thing, by the way, one is truth table. But let's do this, since it's the first time we do this, you can also derive equivalence of these using logical formulas that you already know. Okay, so let's look at, so implication, we convince ourselves, maybe, that it is equivalent to a disjunction of this form, that either not precedent or the consequent is true. Okay, let's look at this implication, the contrapositive of this one. So if I rewrite it in this form, okay, then what does this law tell me? This implication is equivalent to a disjunction of negation of this or that, where here is the negation of the hypothesis in this implication. It's a negation of negated Q. And a consequence in this implication is not P. Well, then I cancel out, because I know that this is a flip and then flip back. So this is equivalent to Q. And boom, I have this, because I know that disjunction doesn't care about the order, right? So whether I say A or B or A, these are equivalent, right? We didn't say this, but like, okay, it's immediate from the truth table, and also you know that. Okay, so when asked, okay, show equivalence of two expressions, you can do them by a truth table. You can do by some sort of reduction and some other argument and invoking some other stuff. You can do them by these type of rewrites. It's sort of, sometimes one is faster because you see quickly how to rewrite something. Sometimes you don't see. And perhaps resorting to like laying out the truth table is the only way. If you're new to this, you're going to do truth tables, and then you will start noticing some patterns, and you will start like being able to rewrite stuff and notice how to eliminate parts that don't care. And you will see, you'll do exercises, and you will see like, oh, here was a way to rewrite it that I didn't notice, but now that I've seen it, maybe I will learn to do that. Here is another operation which we are going to introduce, saying which formula it's equivalent to. It's an if and only if. It's a bi-conditional operator. So it's denoted with the arrows, which goes in both directions, and it's read as P if and only if Q, because so P if Q is this direction, P only if Q is actually a very funny way to say this direction, to think of this. So this is like falling domino thing, that the precedent is true only if consequent is true as well, because to say that P implies Q is to precisely say that, the moment P is true, then Q must be. So P cannot be true unless P cannot be true unless Q was. So P only if Q. It's a funny way to say it, but that is what it means. So we declare this thing to be simply this formula. So we say P if and only Q if to be the same as to say that both of the following implications are true. First, P implies Q. Secondly, Q implies P. And if you look at the truth formula, this would be the truth table. Truth table. This is the truth table. Why? Because you must satisfy both. Now notice, when does this become false? When either this guy is false or this guy. Now this guy is false in only one world. It's the world where P was true and Q was not. It's this row. So therefore, this conjunction would be false in that case. Now the second part of the conjunction is Q implies P. The only way to falsify that part is for Q to be true and P to be false. It's this row. Q is true, P was false. So that guy also falsifies this conjunction. It falsifies this part. So that's the way to construct this truth table. Okay, and if you really did the truth table by the books, that's exactly what you would do. What would happen? I'm just sort of short-circuiting a little bit, shortcutting, I guess. Okay, if P, then yeah, short-circuiting would not be a very good thing, would it? So yeah, all right. Okay, let me maybe look at the, oh, no. So the chat has like derivations of some stuff. So I hope Will is on top of this and, fighting with people like throwing some derivations. Please continue doing that. And I hope you guys are cooking up something good on this chat. Okay, so I'm moving to the next set of slides. They're both posted at the website, right? And as if this second, like I don't remember whether what I'm saying it's 1.5 or 1.6 or still 1.4 in the textbook. Okay, but if you, I mean, after the lecture, I'll just mark it. We got to point 1.7. All right. Okay, so we are we doing on time? Okay, we here are some logical equivalences that we have observed. So conditional as a disjunction, the Morgan laws, the contrapositive, and here are some we haven't touched. So associative laws. So look. Yeah, so the associative laws are sort of actually, that this is sorry, actually we did touch. This is the first one we saw. Sorry about that. That order of when I take a bunch of conjunctions, it sort of does not matter what order I take them, and the same goes for disjunctions, right? So I should have made them right here. Okay, there is more of these laws. And even this does not exhaust the table, of all laws. So, so here is some, like for example, when somebody says either P or P, well, that could be simplified as just P. Okay, it's the only way this can hold is if P was true. Also, to say P and P is the same as to say P. Associative laws we've seen. Commutative laws that order does not matter in conjunction as disjunction. Okay, check. Distributive laws, we haven't seen them. So when you say it's either the case that P or that some conjunction holds, then you can actually see it as a conjunction of either P or Q and conjuncted with either P or R. And the equivalent thing happens when you inversely have the inner operation is disjunction and the outer operation is conjunction. So this will take a bit to like look, stare at the truth table, see that this is true. Why would you ever bother with this stuff? Well, because maybe you derive some things and it looks like that, and now you can take it out and observe, P is true, so I don't need to bother now with this part. Identity laws, when you have disjunctions or conjunction, and one of these is false, then they act in a very predictive way. Like to say that either P or something obviously false is just to say P. To say P or something false, then is to say false, right? So this basically lets you simplify expressions. And also, if you say that both P and not P holds, then it does not matter what P is. If it's a complex formula, you don't have to evaluate it because some part of the expression is equivalent to saying that both whatever this thing is and a negation of that hold at the same time. Well, you know that this cannot happen. This is false no matter what P is. Conversely, if you have an or, then again, you don't have to evaluate what these things are. These could be some complicated cases, conditions, but if you know that some rule is triggered whenever either the condition happens or it does not, you know that you basically can set the value of this gate to be true, fixed, right? And it like allows you to reason about how some sort of system, a Boolean equation involving a bunch of stuff, would behave, would evaluate, right? The Morgan laws, absorption. This is a very funny thing, okay? And I will not get into it, right? It's a very, look, it has only two variables. It's gotta be like, yeah. But think about it. Like, why is that true? And why is that true? Okay, and these rewrites of conditions as disjunction, right? So what's the take from all of this stuff? You don't need to remember the names. You can, like, in some nerdy circles, you can impress somebody maybe knowing them, but the truth is, like, we don't really care. What you should do is to make sure you understand them, make sure you understand how they work, because if you do, then you just understand how all these Boolean operations work, right? And basically, if you do, then they become like, oh, of course, obvious thing, right? So you don't even need to know them, in the sense that you can use them without being aware that you do. This distributive and absorption law is a little tricky. The contrapositive, this expression, like, you kind of have to remember, I would say. And also De Morgan, you should remember, and the contrapositive, whatever that was, you should remember. Well, I guess I don't have it actually here. Now, a little detour. Look, sometimes they're obvious, right? Because basically they correspond. Look, like, we all know that plus and product, it's like from, I don't know, grade 1 or 2 in elementary school. We know that these things hold. But so if you think of Boolean as some sort of arithmetic where you have just zeros and ones, there is a clear correspondence between these things. The place where it breaks, for example, is this one. So if you think of an OR as an addition and as a multiplication, okay, 1 is true and 0 is false, then this one breaks. And the reason is that that actually an OR is not the addition. So an AND, if you think of P and Q true false as 1 and 0, is precisely the multiplication. And actually, you can think of these operations as operations mode 2, right? But well, for the product, you don't have to. It stays 0 and 1, even if you don't do modular reduction. But P or Q is not the same as addition. Where not? Where P and Q were both true, the addition is 2. And now what are you going to do with this 2? If you do mod 2 reduction, right, so you only care about the number is even or odd, then 2 will correspond to false, 0. The XOR is the modular addition, right? And if I place an XOR here, this law will not be true. Okay, it will be violated in the 1-1 case. So what do I do with the can I arithmetize the disjunction, the standard OR, and this is an arithmetization of XOR. What about the regular OR? Well, you can. So here's what you can do. This. So P or Q can be looked at in arithmetics as add them, but then so add or subtract, because mod 2, it doesn't matter which way you do it. It's really an XOR, or an AND, a product. And this is true, right? So if they're both true, if P and Q, whatever values they have, just adding them, thinking of them as 0 and 1, gets you the true value of this junction, which is 1, except for one case where they're both 1s, which gives you to 2. So you have to kind of like kick out that 1. That's what this operation does, because this is a 0 in every other case except of PQ being both 1, right? So this added element will not do anything in all these other cases where you were good already. Okay, so the takeaway is that you could think of this as arithmetics, and you can think of this as arithmetics mod 2. And you can also see that a lot of laws are sort of obvious because they correspond to the underlying arithmetic laws that you all knew. But then some of them do act differently. And that's because disjunction, sorry, is not exactly a plus. Okay. Moving on to a new topic. It happens at some point in chapter 1. I will point out where exactly. We take sort of like a higher level abstraction that we're going to call a predicate. It's a function on statements, on Boolean variables. So let's declare P of x, this function, as a predicate that says x is a prime integer. This is a predicate, is that I cannot evaluate this to be true or false. It's not a proposition. Only if I instantiate this variable with something, then the result is the proposition. So for example, if x is 5, I have a case of P of 5. It's a predicate. How does it read? It reads that 5 is a prime. It is now a proposition that 5 is prime. I can evaluate whether it's true or false. It's actually true. If P of 6, it's also a proposition. It's a proposition that 6 is a prime number. It's a false proposition. It's not a prime number, right? It's 2 times 3. So predicate, you can think of this as a function whose inputs are prepositional, variables, are Boolean variables, and the outputs are propositions. And if you evaluate it for any fully instantiated variable, right, which is either true or false, then the output is it's a proposition. You should specify a domain of when you declare a predicate, you should specify what the domain is. Very often the domain is implicit. For example, when I say that P of X is that X is prime, the implicit domain is rational numbers or even natural numbers, positive numbers, because, you know, for other number, like the statement that it's a prime is meaningless. You know, a rational, which is not a natural, is never, you know, is basically a predicate that makes sense only for integers. And so sometimes it will be obvious from the context what the domain is, but for this understanding how the domain acts and how the statement, truth or falsity of a statement depends on the domain, we're going to make domains explicit. And you have to understand this relation, and you have to understand that the same predicate, like if you it sort of reads the same, but if you declare it on a different domain, it will have different meaning. And some statements involving this predicate will evaluate differently. But think of a domain which includes all the students in a class from A to Z. So a predicate T of X is that student X got an A grade, right? So I can say stuff like T of Carlos and T of Zach, which means that both Carlos and Zach got an A. Or I can say T of Zach implies T of Beatrice. If Zach got an A, then so must have Beatrice. Maybe they studied together, or I know that like Beatrice is just better than Zach. So like if Zach managed, then Beatrice must have. All of these are propositions, right? And you can imagine, like, you know, like in a constraint in a computer system to be declared in this fashion. That if some predicate holds for some domains, then it holds for some other inputs, or you know, rules written using such predicates. Okay, so you have these predicates. They are propositional functions. If I just say T of X, I cannot evaluate the truthfulness of it because I need to know what X is. So if X is a free variable, then I don't know, T of X does not have a truth value. But here is how to fix the truth value, even though you're not instantiating X with any particular value. It's a quantified expression that is denoted by this inverse E, and it reads, there exists X such that T of X, in brackets, is true or holds. Okay, so how do you evaluate the truthfulness of this expression? How do you, I'm saying that when you do this existential quantifier, it's called existential quantifier, then this expression is a proposition now. It has a truth-false value. How? Truth value of this quantified expression would be true if the predicate is true for some value of X, at least one. Okay, that's what it means, right? There exists some value which makes the predicate hold. By the way, this value must be part of the domain of this predicate, right? So if the domain of the predicate was something else, the fact that there exists a value outside of this domain does not mean anything. Again, both in this quantification and in predicate definition, there must be an explicit domain. If you don't write them, assumption is that quantification here is over the same domain that the predicate was declared over. Okay, but there is a notation which could also say, okay, in spite of this, it was declared on some domain, I'm going to quantify for all X's in some other domain where it would only make sense if that was a subset of the original one. Okay, so it's true if there is at least one, And conversely, it's false if that statement is not true. What does it mean? For all the x's in the domain, t of x is false. Okay, so take a domain of positive integers, right? And say there exists an x such that its square is x. Well, that statement is true, right? Because there does exist one integer in this range. It's a 1, and it's true. It's false for all the others. Like, take any other integer larger, and its square is greater than itself. This is indeed the only one for which, and this is true not just for integers, it's actually true for rationals, it's true for reals. The graph of the quadratic function is going to intersect, oh, actually a 0 is another point, right? So it is true. If the domain excluded either 0 or 1, then this statement will be false, right? Because x equals 0, x equals 1 is the only even reals that satisfy it. Okay, let's look at this. There exists x such that x plus x, so 2x, is equal to x. Well, you're going to solve this. When is that? When is 2x equal x? Well, the only place that means is that x is 0, right? Like, subtract x from both sides and you got x equals 0. X equals 0 is not in your domain, so it's false, right? If the domain was defined to include 0, then there exists an x implicitly in that domain, which would make the statement true, becomes true. So extremely sensitive to what the domain was. Universal quantifier. This v with the little dash is read for all x, t of x is true. Okay. I read these statements differently. This guy was, there exists x such that t of x is true. And this one, for all x, I guess a comma, t of x is true, right? That's how we read these. I mean, you know, other forms just don't read well in English, right? Perhaps in other languages, they map more similarly. So now, how do you evaluate truthfulness of this expression? Universally quantified predicate is true if the predicate holds for all inputs in the domain. Conversely, it's false if at least one value of the element from the argument from the domain, the predicate is false. Okay, which corresponds to what we say in English, right? Like when we say for all x, it holds that t of x. Yeah, it says exactly that, and a violation of it would be exactly this. If you say, okay, I'm going to show to you that this formula is wrong. How do I falsify this quantified expression? I need to find a 1x which violates this predicate. It's often called counterexample. Okay, falsifying a universal quantified expression is easier than showing that it's true. If it is true, then you have to somehow see that this predicate actually holds for every argument. It's like often like some sort of mathematical law, or like it's a non-trivial fact that you have to prove. Okay, or perhaps it's a logical formula which after you evaluate, you see that basically it always comes out to true, and you can argue about it with some rewrites or truth tables. But negating is easier. Find a counter argument. Conversely, here, showing that this is true is easier than negating it, right? Than falsifying it. Showing this is true, you have to just show 1x that satisfies this. To falsify this is very difficult. You should show what? That every value of x makes T of X false. And perhaps as I say this, you can already see now laws between what does it mean to falsify, to negate a quantified expression. You are actually moving to between the two different quantified expressions. You will see this in a second. These are De Morgan laws. So let's look at the example. So predicate is x squared is x. It's the same as before. Is it true that for all x's it holds? No, right? Because now we need to find one that falsifies it, and it's easy. Again, if the domain was restricted to bits 0 and 1, oh, actually it's true for all of them, all of the two of them. Yeah. Okay. What about this? X squared is always at least x. It's actually true if the domain is positive integers, right? The smallest positive integer 1 is already true because it's the equality. For all the others, it's even more true, right? Because it's a strict inequality. What about this one? Well, it's false because there exists one element x which falsifies this predicate. That element is 1, x equal 1. That's the only one that falsifies this predicate because it's an equality and not strict inequality, right? Existential quantifier over if the domains are finite, or you can enumerate the domain. Okay, so there is like x1, x2, x3, x4. Okay, these are all the x's. Like in the case of a class, you know, here there's 26 or 27 students, right, for one letter of the alphabet. If I say there exists an x such that the x over this finite domain, you can be rewritten as this big disjunctive clause. It's either true. What I'm saying when I say that there exists one that satisfies the predicate, what I'm saying is that either the predicate satisfies at first, or at second, or at third, or for all the elements in the domain. So the existential quantifier is really one big disjunction. Universal quantifier is one big conjunction. What I'm saying is, I say that for all x's, the predicate holds. I'm saying it holds for Ahmed, it holds for Beatrice, it holds for Carlos. It's a big conjunction. And therefore, okay, so let's, okay, sorry, I forgot about my logic here. All right, let's look at quantifying expressions that are predicates, but they're not explicitly predicates. So what if I say I have some predicate p of x, that's x is prime, and g of x is an odd number. Okay, these make sense for integers, for integer domain, or even positive integer domain. So what about the following compound expression? P of x implies d of x. Actually, you can define this as a predicate. The predicate, let's call this predicate I of x for this implication to hold. I of x holds whenever P of x implies d of x. And I can therefore say for all x, this implicit I of x predicate holds, which means that for all x, P of x implies d of x. Now, is it true or is it false? Right? Let's think of this a second. Is it always true that if a number is prime, then it must be odd? Okay, here is the one and only one case that violates it. 2 is a prime, it doesn't have divisors, and yet it's not odd. All the other primes must be odd. Yes, if you took a number that is even and higher than 2, then 2 is a factor, so it cannot be prime. And it's sort of natural, okay, and if the number is prime, so it doesn't have divisors, so it doesn't divide into 2 in particular, so it is an odd. Yes, but this case, divided by 2, it is true. Yeah, okay. So this implication predicate would be falsified at this case, right? The implication is not true when I instantiate with the 2. It is not true that if 2 is prime, then 2 is odd. It's an odd implication to state. But think of it, I'm saying if 2 is prime, then 2 is odd. Did I say true or false? 2 ways to look at it that this is true. It is, if 2 is prime, then 2 is odd. It is false, right? Because 2 is prime and 2 is not odd. Yeah. Okay. So this is the case where this implication is falsified. What about this guy? Okay. So if a number is prime, then it's either odd or it's equal to true. Okay, we kind of don't have to do this again. It is true now because that's the only case that violated this implication, right? So once you added to the consequence that you allowed yourself this sort of safety valve that this part is true if either this or x was true, x was 2, yes, then now you cannot violate this. It's always true. Yes, for all primes, indeed, they're either odd, these are all primes greater than 2, or that prime is a 2. What about this one? For all x's, if x is smaller in negative, then it's a prime. Well, x's negative are not in the domain. So this part, the precedent, right, will be violated, will always be false for no matter how you instantiate x. This part will bound to be false in this domain. So over this domain, to say that if x is smaller in negative than it's a prime is to say same say as if something obviously false, then x is prime. That's true. Why? Because an implication becomes true the minute hypothesis is false. You don't need to worry about the value of the consequence. Sometimes for some x's is true, for some x's is false, but none of these x's satisfy this, and therefore for any x, this implication will be true for any x in this domain. Okay. Why would I say that? Who would say that? Okay, maybe they wouldn't, right? I mean, it's only kind of they want to trick you. The point is, you need to understand how these quantified expressions and how implications work. This will have implications in a system, say, that is defined by a bunch of constraints and bunch of logical laws on it. And you need to understand that if the law says, if something starts, then something else happens, and this something is not true, then you just like you go over this. It's this satisfied. This constraint is satisfied in your system. Oh,
just a heads up, it's after 1.
Yes. Good. So good. So that's where we will start the next time. I will stop recording.